Students, this is Unit 2, Segment Lines and Angles, Lesson 2.4, Informal Proofs with Segments. You're taking a look at this page right here, and you are recording your date, time, location that you are doing this, as well as getting a parent or guardian sign off. So this page, you want to take a stab at this completely on your own. Notice the squeeze the sponge. I don't tell you what to find. I ask you to find everything that's possible. Pause the video, restart when you're done. Make sure you have a red pen handy. Actually, it says right here, you try. We're going to do one together. Excuse me. Let's do one together, and then you do what you try, just as a quick review. I didn't notice the U try. It says, given collinear points, L, K, and J, find everything possible. So let's look at the relationship that we have here. We know that the relationship of L to K, there's no midpoint here, plus K to J is going to be equal to L to J. Now notice, I always start with what's called a thing equation, a thing equation. You talk about the relationship of things before you talk about algebra. Geometry is about the relationship of things, segments, angles, shapes, polygons. Those are physical things. You want to think in terms of things prior to doing the algebra. Color coding is also very helpful for this. So now we know we circle, plug, chug. We have LK, and we come over here and we do 2x minus 10 plus so we have LK plus KJ equals LJ. That's 2x minus 10 plus 7 equals x plus 3. We collect like terms, and we're going to solve here. So you do your own algebra and just look up, and we'll probably be done about the same time. Okay, look up. Woo, x is 6. You think you're done. You got a whole number, and you're all happy because it's not a fraction. You don't have to second guess yourself, and you think you're done, and you're not. Because I didn't tell you to just solve for x. I told you to find everything possible. Watch out for that sponge, because if you don't pay attention to that on a test, you might think you're all done just because you solved for x. And if this was an algebra class, that's perfectly fine. But this isn't algebra. So you have to ask yourself, what else can you do? Well, now that you know it, we can plug it in and find some stuff. So we can do right here, L to K is going to be 2 times x, which is 2. So we just found L to K is going to be 2. We already know K to J is 7. That means this should come out to be 9, which if we stick 6 there, it actually does. So that's nice. You can really check these by finding everything, and we can see that 2 plus 7 does equal 9. It all fits. So there's an example of how I want this done. Now this one, you do on your own. Pause. Welcome back. Again, if you were smart, you talked about things before you got into the algebra. So B to C plus C to D equals B to D. And notice if you color code it, it also helps a lot. So B to C, we're going to come right down here, plug it in. 2x plus 15. B to D, circle, plug, chug. Collect like terms and start solving. Should have gotten x equals -6. Now, don't stop there. We have to see if it actually works. So 2 times -6, that's going to make that -12 plus 15, which is going to equal +3. We already have the 8 there. Let's take a look here. 17 plus -6 is going to be +11. Now check your work. From here to here is 3. That's 8. 3 plus 8 is 11. Check. You're done. So in today's lesson, we're going to read. By the time we're done, you're going to be familiar with this concept of reasoning, symmetric, reflexive, transitive, proof, justification. Now, don't freak out with these words, proof and justification. If you've heard rumors about geometry and proofs, I promise you, you're going to do fine. But learning how to justify your work and reason through what you're doing and answer that question, why, is critical to a variety of professions. So doing this in a math class will actually help prepare in a lot of different types of professions, even if it's not directly related to geometry. Any kind of profession that deals with research. Actually, writing any sort of essays in which you have to justify your thesis. Obviously, anything in the legal realm, you have to justify when you make certain statements, give reasons behind each of those. So learning how to reason well is really important. And we've actually already done this. I've already introduced this to you without you even realizing it, because we've done these where you have the how on the left and the why on the right. Let's do our algebra together on the left. Ready? Circle, distribute, circle, distribute. And the reason we're able to do that step would be the distributive property. We're going to collect like terms. Technically, where we were adding on one side with the equal sign or subtracting on one side, then the other. So that would be what we just did, was addition and subtraction of real numbers. Ready? Let's start getting n by itself. So I'm going to do this. And our next line reads, and what we did is we added both sides, so that's going to be the addition now property, because we worked on both sides. We subtracted both sides. And then we divided both sides. So I've already introduced the concept of what's called reasoning and justification to you, using what you're familiar with, and that is algebra. Now, for this particular section, it is super important that you are incredibly observative, incredibly observative. So what I want you to do is that for the next 2 minutes, I want you to look from top to bottom, and your goal is to find as many changes as you can in 2 minutes. I have a timer set for you. I'm just going to let it run here. Ready? 2 minutes. Find as many changes as you can. Go. Okay, students, I have a little bit of a challenge for you. It says there's 9 changes. I myself gone through this about 3 times. I'm only spotting 8. So let me know if you find that 9th one, and I'll give you 1 point extra credit. Let me tell you, now if you get less than me, that's not an issue. I can find 8 of the 9. Let me point out the 8 of the 9. 1 is glasses, no glasses, right there. 1 is glasses, no glasses. 2, no smile and smile. No smile and smile. 3, color change from this to this. Color change, if you look very carefully. 4, right here, glasses change. Glasses, no glasses. Glasses, no glasses. This was a subtle one. Right here, she's writing with her right hand. Her right hand, and this one she's writing with her left hand. That's number 5. This one, looking at the colored slide again, there was a color change from here to here. That's 5. 6, there's a person completely missing. That person down here is completely missing. 7, another color change. Stripes to blue stripes. Right there, that's 7. Which one where's my 8? Do I only have 7? I thought I counted 8. I lost track of my count here, but I counted 8. Oh, I didn't count. That's 5. This should be 6 here. 6. And then this is 7. And this was number 8. So you tell me where the 9th one is. I'm really curious. Now, on that note, again, it's all about being very close observers. That's the whole point of the next section. You need to go in your reference booklet, please. And we're looking at these 2 pages. We're going to do some problems together. So in your reference booklet, segments on a coordinate plane, this is where we left off. We'll come back to segments on a coordinate plane. You already know that, midpoint, slope, and distance. I want you right here where there are segment properties. Segment properties. Ready? Last class, we added segments and we did midpoint of segments. Now we're going to talk about segment properties. Remember here, now here are your algebraic properties. Algebraic properties, and many of those properties also apply to segments. So keep that in mind. Those algebraic properties actually apply to segments. And there are three more you need to be familiar with. The first is that segments can be symmetric. Symmetric. In other words, the distance of P to Q is the same as Q to P. That's called symmetric. Not to be confused with something called reflexive. Now watch very carefully. Let's label this. When a segment is shared by two shapes, so these two triangles, let me color code them. We have a green triangle on one side and a yellow triangle on the other. This segment here, AB, is shared between the two. We actually mark it congruent and we write it like this. AB, the segment, is congruent to AB, the segment. That's called reflexive. Reflexive. Let me give you another example. If you have colors, this is helpful. Here we have a triangle EFG. Switch colors. And another triangle HGF. If you look very carefully, this segment FG is shared by both those triangles. That's all, again, called reflexive. So we would write it like this. FG is congruent to FG. So segments can be symmetric, reflexive. Another one is transitive. Transitive. This is pretty common sense. It means that we can say this. If PQ is congruent to QR. So I'm just going to write if PQ is congruent to the segment QR. And you also knew that QR was congruent to RS. Notice very carefully the repetition of QR. And on the segment itself, you can see there's an overlap. Therefore, we can conclude that PQ is congruent to RS. We transfer the congruency. Therefore, those three dots mean therefore, PQ is congruent to RS. That's called transitive. This one we did already. It just, segments can be added. So segment JK, the distance between J and K, plus the distance K to L, equals the distance J to L. Pretty common sense. Segments can be added. Little segments add up to big segments. And last but not least is that when segments have a midpoint, so put your hatch marks on there. Nice sound effect for hatch marks. We know that segments become congruent when there's a midpoint. So if M's a midpoint, we know that X to M, the segment, is going to be congruent of M to Y. Now, in your reference booklets, we're going to do something very similar to what we did in your preview notes. So here's your preview notes. Right there in the beginning, we did something where we had the how on the left and the why on the right. We did the how to do it on the left and the why it is allowed on the right. Now, in your reference booklet, we're going to do something what's called a proof. Don't freak out. It's not hard, I promise. But when you do proofs, I always want you to follow what's called gift. Number one, you mark what's given on the diagram. So put a little G for given. Then you mark what's implied by the given. Then you mark what's called freebies. Freebies are things that are true even if they're not in the given. Things that are always true even if it's not in the given. Those are called freebies. Last but not least, think through, better yet, talk through how you can get from the beginning to the explain. That's where we're going to get our acronym GIFT. See this symbol here? Very important. No naked diagrams. Do not leave your diagrams what I call naked. You need to learn to interact with your diagrams physically, better yet in color code. You'll see that in just a moment. Have some color, Sandy. It will be very helpful. On a test, if your diagrams are completely naked, untouched, untraced, you will get marked down. Because geometry is about the diagrams. It's not just about filling in blanks. Let me give you an example here. Let's do this one together. Get your colors out. They're helpful. We are given some starting information. We are given that the segment AD is of equal distance of C to E. So choose one color for that. And we're just going to bracket it A to D. And C to E is equal. So hatch, hatch. Switch colors. We also know that BD and DE are the same distance. So B to D and D to E are the same distance. Notice the double hatch. That's what's called our given information or our starting information. What we're going to try to prove is the fact that the distance, given this scenario, the distance A to B is the same as the distance C to D. I usually do what we try to prove or explain in red. I'm going to put a question mark there. How do I know those are equal? Well, it's pretty common sense. The longer one minus blue minus the green gives you the red, right? You kind of think it through. The blue minus the green gives you a red. But we have to say that with a lot more detail. So watch what we have going on here. Let's start with something simple. We know that the distance, keep your color CAD, A to D, is the same, equals A to B, which is the red, plus B to D, which is the green, in my case. We know that the big segment equals the little segments added together. That's called segment addition. We also know that C to E is the same as C to D, that's the red, plus the green, D to E. Watch very carefully. Little segments add up to the bigger segment. Again, that's called segment addition. This is where observation is incredibly helpful. That's why we did that little game earlier. We know AD and CE. Watch your colors. That's the blue. Are equal. Why do we know that? It's simply given information. Now, this is where it gets interesting, and this is where you really have to look in your observation skills. Ready? I'd like you to box this, please. Box it. I'm going to pause. And I want you to look up and find that exact same expression and box it. I'm going to pause for 5 seconds. You should have noticed that that is the same as this. Ready? Now I'd like you to circle this. I'm going to pause again, and I'd like you to circle where else do you see that expression. You see it right there. Now you ask, what happened? We took this AD and we replaced it with the orange. And we took this C to E and we replaced it with the green. We took the bigger segments and we replaced it with the smaller addition segments. That's called substitution. We substituted one for the other. Now look here, BD and DE are equal. How do we know that? Look real carefully. That's also in the given. And this is where the fun part comes in. Look really carefully at 4 and 6. There is only one change. Circle it. Look really carefully. There's only one change between 4 and 6. Only one. Spot it. Ready? Did you catch that? Everything else is exactly the same. That's the same, that's the same, that's the same. We took out BD, we replaced it with DE. Why can we do that? Because here we said they're equivalent. Again, that's called substitution. Now look at what we have on both sides. See this? We have DE on both sides. You would subtract DE both sides like you were trying to get rid of it. You'd end up with, ta-da, what you're trying to prove. Let me shrink this back so you can see it. See that? We're trying to prove that that segment A, B, and C, D are equal. What did we do between 6 and 7? Subtraction property. All right, go back to your video notes, and we're going to do another problem together because I know you need more practice on this. Don't freak out. You will get better at this. I promise. I promise, I promise, I promise. Ready? I'm going to do 2 examples together, and I'm going to do both of them with you. I'm not going to let go of your hand right now. You're not doing anything by yourselves. Just follow along. Have your colors handy. So another example. We read our given, and we mark it on the diagram. We read the fact that CE is of equal distance to DF. Choose a color. Now trace. CE is of equal distance to DF. That's what we're given. We're trying to prove that this, given this scenario, that the segment C to D is of equal distance as E to F. That would be the red. So given these larger overlapping segments are equal, the blue, we're trying to prove that those red segments are of equal length as well. So we've marked on the diagram. It's kind of implied. If you look really carefully, just kind of highlight. We're going to overlap right there. Now we just kind of talk or think through. I'm going to talk this out loud. If you notice the blues, if the blues are equal, if we were to take away the overlap, look what I'm doing. If we were to take away the overlapping piece, what would be left would be the red. So of course it's equal because we take away the same thing. You notice that? The logic behind it? If the blues are equal, and you take away the overlap, the red left behind has to be the same because we subtracted the same from both. So it's a good idea to talk yourself through it. Ready? Now we're just going to document what we know is true. Watch carefully. Color code with me if you can. DE is equal to DF. We know that because it's given. CE, this segment right here, is equal to C to D, that's the red, plus, I just changed the color to green so it's easier to see, DE. Why do we know that? That's called segment addition. Let's take a look at what we have here. We also know that DF, the big segment, DF, is equal to the segment DE, again, I did that in green, plus EF. Why do we know that? That's called segment addition. Very carefully, it's number 4. There's nothing on either side, so look at what your target is. Our target is to say that the red segments are equal. Our target is to say that the red segments are equal. So we have to do something that involves the red segments. Watch very carefully. We already saw in step 1, CE, circle that, and DF, box it, are equal. And if that's the case, we can say that this expression is equal to that expression. And what we did is we substituted, since we told in 1 it's equal, and these equal those expressions added up, then number 4 we substituted. Call that substitution. Now, you ask yourself, from 4 to 5, what is the only change? 4 to 5, what is the only change? Let's get real close. The only change between 4 to 5 is that we subtracted DE both sides. And we were left with what we're trying to prove. We don't say the prove. We have to ask ourselves what changed. And what changed was we subtracted DE. So we call that subtraction property. I know this is very new to you, so let's do another one. Take us 5 minutes. Please keep those colors handy. Colors are very, very helpful. Once again, you may not have naked diagrams. You guys have been trained to fill in blanks. I do not want you immediately going for these blanks. That's a no-no. This is not fill in the blank algebra. This is geometry. Your focus is actually on the diagram. The star of the show is the diagram, not the blanks. We don't want to have naked diagrams. It's embarrassing and it's bad math. Okay, ready? Get your colors handy. I'm going to trace it with colors, what I have. We know the segment AB is equal distance as CD, so use whatever color you want, just be consistent. We're also told that the distance B to D is the same as D to E. I know the blues are equal and the greens are equal, or whatever colors you got going on there. We're trying to prove that those little segments, if they're equal, then the bigger segments are equal. So I'm going to trace those bigger segments, and I'm trying to prove that they are equal. And my prove, I always use red, because that's like a target. Okay, so let's see what we can do here. Just be observative. AB and CD are equal. Why do we know that? It's in our given. Number 2, there's a blank on both sides. So you go down to number 3, and in number 3, we start talking about segment AD. The little ones add up to it. So before we can do that, we have to talk about the other given. So number 2 is going to be the other given. We have to say these segments are equivalent. That's also given. Okay, now AD, that's the red. This big guy is equal to the blue and the green added together, or whatever colors you're using. And we know that's true because little segments add up to bigger segments. We can solve that segment addition. Okay, now here's where it gets a little tricky because you have a blank here and we're taking a look at number 5. So you have to look very, very carefully. What happens between 3 and 5? Ask yourself, what's going on there? What's changed? So somehow we've talked about AD equals CD and DE, and if you look really carefully, what has changed is what this is. You see that? That's changed, and yet this has stayed the same. So we have to ask ourselves, what do we need to say before we can swap out those two things? And what we need to talk about is way up here is CD. The segment CD, excuse me, or not the big segment, C to E. The segment C to E equals the blue and the green added together, which in this case is going to be CD and DE. See that? And why can we do that? That's called segment addition again. Now, why did I need that? Because look really carefully. Lo and behold, these match. These match. So you ask yourself, what happened between here and here is we took this and we swapped it out with that. And we replaced it. And that is called substitution. substitution. Now look at what we're trying to prove. We're trying to prove that AD and CE are equal, which if you look very carefully at 4 and 5, you're going to notice something. This is exactly the same as that now. Do you see that? Exactly the same. So if those are the same, these can be the same. Why? Because you can swap out this and replace it with that. That's called substitution. Now, I know this looks a little freaky. Don't worry. We'll get lots of more practice in class with these. Lots of more. I'm not looking for complete comprehension. Great job hanging out with something that's very new. Good perseverance.